When I was in high school, I liked to hand my Android smartphone to my friends and show them my pattern password, then watch as they spent the next 10 plus minutes struggling to recreate it, often ending when they made enough incorrect guesses to lock themselves out. And you might remember one of the winners of 3 Blue 1 Brown's Summer of Math Exposition Number 1, this video by Dr. Zai, also about Android pattern passwords. Now, I'm not trying to piggyback, I just also have another puzzle involving Android pattern passwords. So the rules here are the same, but we're playing a different game. And in case you don't remember these rules, here's a quick refresher on how Android passwords work. Order matters, and you can't go back to a dot you've already been to unless you're just passing through on your way to a dot you haven't been to. So when I showed my friends my phone password, all I did was show them the pattern needed to unlock my phone, without telling or showing them in what order the dots had to be selected. This should be an easy puzzle. I mean, all you have to do is connect the dots, right? For instance, here's an easy pattern to solve. Just go around clockwise, or maybe counterclockwise. Now, as this example shows, it is possible that multiple orders can achieve the same pattern. Then we want to be able to find all possible orders that lead to a given pattern so that we can unlock the phone, no matter which order the owner used. But this isn't the only thing making the puzzle more challenging. Here's an example of a more challenging pattern. Feel free to pause the video and try to find a solution. Now here's 6 additional challenging patterns, and 2 decoys with no solutions. Again, take your time and pause the video to try to solve these. Okay, hopefully you found solutions to at least a few of these patterns. If you spotted the decoys, nice work, here's a trophy for you. In any case, I think it would be nice to have an efficient algorithm guaranteed to find all of the possible solutions. Oh wait, that's the whole point of this video. We can of course just guess and check, iterating through every possible order, but this isn't very efficient, and there's clearly an underlying structure of the puzzle that should help us find solutions more quickly. For example, let's think about the last point of a puzzle. Going back to our rules, no point can lie in an earlier segment. Therefore, because the last point is last, it can only lie at the end of the last segment. For instance, in this pattern, only one of these 3 points could possibly be the last point of the puzzle, because all of the other points are on multiple segments or in the middle of a segment. Now, let's look closer at one of these points, the one at the top right corner. If we assume this is the last point in the order, what was the second to last point in the order? It had to be on this line segment somewhere, but which of these 2 points did we come from? To answer this question, let's back up and think about how we can extend existing segments in general. There are only 3 ways to extend a segment after drawing part of it. We can continue moving in the current direction, we can turn around, then extend past the beginning, or, if the grid is larger than 3 by 3, we can leave the segment, come back, and then connect 2 points on either side of this section. In each of these cases, there's one key thing to notice. The process ends by covering the entire segment from one end to the other end in one continuous motion. So what does this mean? This means that every segment is traversed from one end directly to the other in one continuous motion. Let's go back to our example. If we assume the top right corner is the last point in the order, then we know the segment at the top was traversed in one continuous motion, so we must have come from the top left. But then the segment on the left was traversed in one continuous motion, and the top left can't be the starting point for 2 segments, so we must have gotten here from the point at the bottom left. And this must have been drawn immediately before the line at the top. But then similarly, the segment at the bottom was traversed in one continuous motion, so we must have come from the bottom right point. So we must have gone from the bottom right to the bottom left to the top left to the top right at the end of our order. In other words, we can work backwards from the end by connecting endpoints of segments to partially solve the pattern. But now there's no other segments with the bottom right corner as an endpoint. So where did we come from? Well, we must have come from a point on the same segment. So the middle of the bottom row is the only option. Continuing to work backwards, we know the middle vertical line was drawn in one continuous motion, so we must have come from the top middle point. Now again, the top middle point isn't an endpoint of another segment, so we must have come from another point on one of the segments passing through this point. Because this is a 3x3 grid, all these segments will be completely used up by their own endpoints and this midpoint, except for the segment we most recently added to our in-progress solution. So we must have come from another point on the most recent segment, in this case, from the center of the grid. Then this is an endpoint of another segment, and this segment was at some point drawn from end to end, so we must have come from the point on the right. This is not an endpoint of a segment, so the previous point must be on the most recent segment, but no such point exists. So there is no previous point, meaning this is the first point in our solution. And indeed, we're done. We found a valid solution in reverse order. Passing through the points in this order does result in the correct pattern. So let's review this process. First, we identify candidates to be the last point in the order. Then we choose one and move backwards through the endpoints of segments as many times as possible. When we get stuck, the previous point must lie on the most recent segment of our in-progress solution, and we repeat this process. When we cannot repeat the process, it's because we're done. But what if our guess in step 1 is wrong? As a test, let's look at the same pattern, but assume the last point in the order is the middle right point. If the middle right point is the last point in the order, then our process of connecting endpoints of segments tells us the previous point was the middle of the grid. This isn't the endpoint of another segment, so we must have come from another point on the most recent segment of our in-progress solution. But there are no other available points on this segment, so the center of the grid must be the first point in the order. We're done! But, of course, this isn't a valid solution. All we did was draw a line segment. So our process works if we start from a possible endpoint, and it fails if we don't. It's easy to check if the process worked by checking that the output order correctly draws exactly the entire pattern, and then we can simply keep guessing which point is last until we have a correct order. So now our algorithm is the same as before, except we guess a new last point candidate every time it fails. And if we run out of options for the last point without reaching a solution, then no solution exists. So this is great. We have an efficient algorithm that finds a solution to a given pattern. Let's give ourselves a trophy to celebrate. Except we're not quite at our destination yet because we wanted an efficient algorithm to find all solutions, not just one. Luckily, that's the rest of the video. We must now ask ourselves how our current algorithm will miss solutions. One gap is that our algorithm terminates when it finds one solution. So we could just make it not terminate and keep guessing candidates for the last point until we've guessed all of them. However, the structure of the puzzle makes it possible to find the other options without so much guesswork. In step 2 of our current algorithm, we connect endpoints together because all segments must at some point be traversed from end to end. In other words, segments that share endpoints must be drawn one after another in every solution. So we can break up patterns into chunks of segments which share endpoints. In our algorithm, we guess what the last chunk is, then work our way to the beginning. And we only move from one chunk to another by traveling to the center of a segment and then to one of its endpoints. On a 3x3 grid, this is the only way to move between these chunks. But in any solution, the points at the center of these segments must come before the segments are drawn. Therefore, every possible solution passes through the chunks in the same order. Thus, we can simply find one solution, choose the point at the other end of the last chunk, and then continue with our algorithm as usual to see if this results in another valid solution. In this case, this does result in another solution, which is the mirror image of the solution we found before. How else can our algorithm miss solutions? Step 2 only adds points at the other end of a segment we still need to draw, so this is always necessary to fully draw all segments of a pattern. Step 3, on the other hand, adds points on lines that are already part of our in-progress solution, and then it returns to step 2. But what if we return to step 2, then step 2 does nothing more? To illustrate this, let's return to the example I used at the beginning for an easy puzzle. Of course, we can still solve this by going around clockwise or counterclockwise, but let's look at a solution our algorithm will find. If we guess that the center of the grid is the last point in the order, then connecting endpoints will retrace the entire pattern. And then, step 3, we will look for points on the most recent segment, which is the segment at the top, and we'll find the center of this segment. So we'll add this point to the order. This isn't at the end of another segment, so returning to step 2 does nothing, and we've reached a third valid solution. We can draw this pattern by starting in the middle of the top segment, then moving to the left, and then back around clockwise. We can of course return to the clockwise solution by dropping this point. In general, if step 3 adds a point, then step 2 does nothing. This is because the beginning of the solution involves starting at the center of a segment, traveling to one end, then traveling to the other end. Then we can create another solution by ignoring the first point and immediately drawing the segment from end to end. There is no other way for our algorithm to miss additional solutions, so now we can construct an algorithm to find every solution. First, use our original algorithm to find one solution for a given pattern, then proceed through these 2 checks to find all of the other solutions. And now we've reached our goal. Here's a trophy. Thanks for watching.